Hello. So today I am going to show you how to solve my latest puzzle called Killer Blister. It's a combination killer and little killer Sudoku, and I created it based on an initial spark of an idea I had, which actually Philip Newman helped me come up with a nice intro that uses that idea, and then I fleshed that out to a full puzzle. So thank you, Philip, for helping out with that. And as you can see, right now we're looking at a blank grid, and the reason for that is I am going to be going over a little bit of theory before I go over the actual solve. But before I do that, this is, I guess I can show you, this is what the puzzle looks like. So I'm going to go over the rules, and then you can check the link below to try the puzzle yourself before you watch my solve, if you'd like. So what are the rules? Well, like I said, it's standard killer and little killer. So we have killer cages, which are these dotted rectangles or shapes, the shapes with the dotted lines around them. And so those are called cages. And within a cage, the digits that are placed within the cage sum to the little value in the top left corner. So whatever these three digits are, they would sum to 18. And then additionally, digits can't repeat in a cage. So for this cage, that doesn't matter. But say this 7 cage here also doesn't matter because it's in a column. But this 38 is a good example. By normal Sudoku rules, I could put a 9 here and a 9 here. But because they're in the same cage, they can't repeat. So that is killer. We also have little killer, which are these clues outside the grid with the arrow. So looking at, say, this 12 here. If you look at the direction the arrow is pointing, it's pointing along a diagonal. If you take all the cells in that diagonal all the way across the grid, those digits will sum to the clue next to the arrow. So in this case, 12. So these 4 cells would add to 12. There's no rule about repeating. So as long as Sudoku rules allow it, you can repeat. So this could be a 1, this could be a 1, and this could be a 1, for example. As long as you could then make it out to 12. So those are the rules. Again, if you check the link below, you can try the puzzle yourself. Again, this is a puzzle I made, so obviously my solve will be a walkthrough solve. But please do give it a try. I think it's a relatively approachable, based on the feedback, killer and little killer. So if you want to practice those constraints, it's a good idea. There's no extra constraints to get in your way, no crazy diagonal constraints or anything like that. So do give it a try. Let me know how that goes. And if you get stuck, feel free to watch this. And if you're not able to break into the puzzle at all, perhaps a little bit of theory that I'm going to do before I start the solve will help you out. So please do try the solve first. And when you come back, I will start the solve. So like I said, I'm going to start with some theory. So I'm going to use a blank grid for this. And I'm just going to use the center. Yeah, the center 3 boxes just because it's convenient, but this works in any 3 boxes in a row. So if they're in a row, it's a band, or if they're on top of each other, it's a stack. It works for any band or stack. And what we're going to be talking about is roping. I have talked about it on this channel before, especially I'll link it up there. Is my video on the 666 puzzle by Philip Newman, which was an anti-crop key. So, but I'm going to go over it in a little bit more detail here. And, well, less detail, but more specific to non-anti-crop key. So just general classic Sudoku. What we can think about is, in these 3 cells, there will be 3 digits. Hopefully that's pretty obvious. So whatever those 3 digits are, we're going to call them 1, 2, 3. I mean, we don't actually know what they are, but we could remap it to be 1, 2, 3. So, you know, these are any 3 numbers. So what would happen if down here I repeated those same 3 numbers? I repeated the 1, 2, 3. Well, the result in box 6 here, this 3rd box in the band, is that 1, 2, and 3 can't be in these 6 cells. So they're forced to be in these 3. Hopefully that much is clear. So as soon as we have any 2 rows of the band within a box containing the same 3 digits, those same 3 are then forced to be in the 3rd row of the 3rd box. So say I put the 1, 2, 3 here, that would then force a 1, 2, 3 here. I'm going to switch back to this just for convenience sake. So with these 1, 2, 3s, now we can talk about, okay, what about another one? Well, here we're going to have 3 numbers that are different than 1, 2, 3, and there'll be 3 distinct numbers in these 3. So we could call those 4, 5, 6. Again, whatever they are, we're just calling them 4, 5, 6. Well, now I can actually finish the entire stack, or the entire band. So if you think about this row here, or the, you know, let's just fill these 3, just for the box, have to be 7, 8, 9. And then for this row, these 3 have to be 7, 8, 9. And so then here we can finish this box with 4, 5, 6. And then here we can finish this row with 7, 8, 9, and finish this with 4, 5, 6. So just by putting the initial seed of 1, 2, 3 here and 1, 2, 3 here, I've forced this band to be what's called roped. And if we were to highlight these in different colors, let's say we'll make this orange, we'll make the 4, 5, 6s green, and the 7, 8, 9s blue, then you can kind of see how it kind of looks like it's weaved like a rope. So that's why it's called roped. And so again, that means that we have the same 3 numbers in all the oranges, the same 3 numbers in all the greens, and the same 3 numbers in all the blues. So, and that is caused just by repeating the same 3 numbers, just these 2 repeated, forces this pattern to happen. And of course, we could switch these 2 boxes. And so instead of having the 1, 2, 3 here, the 1, 2, 3 could be here, and then it would rope in a slightly different way, but it would still be roped. So the kind of opposite thing we can think about is, what if I have a 1, 2, 3 here and a 1, 2, 4 here? Well, the 1 and the 2 are going to not be able to be present in these 3. So we have to have a 1 and a 2 down here somewhere. But then what could the third number be? Well, I couldn't make it a 3, because if you look, that would force a 3 into here, and there can't be a 3 here. And I can't make it a 4 for similar reasons, because that would force a 4 up into here, and there is no 4 there. And so it has to be a distinct number with the 1, 2. So we have 1, 2s repeated down here with a 3, a 4, and then something else, which I call 5. And so this forces the entire band to not be roped. And so you can't have the same 3 repeated anywhere in this band. So if I were to put 4, 5, 6 here, well, I couldn't put it there because the 1, 2, 4. So let's put something reasonable here. 4, 5, and 7. Sorry, 5, 6, and 7, right? If I put 5, 6, and 7 here, then I couldn't put 5, 6, 7 anywhere else. Obviously, I couldn't put 5, 6, 7 anywhere in this box because there's already the 5 used. But if I put 5, 6, 7 here, I now have the 4 repeated. So you can see that, or sorry, not the 4 repeated. If I put 5, 6, 7 here, then I don't have any repeated digits, but I'd have to put the 3 up here, and the 3 is already used. So it just doesn't work. So I'm sorry if that was a bit long-winded, but I wanted to sort of explain that theory a bit because it's important for this puzzle. So, and I guess something to point out is, knowing this information just sort of streamlines a solve. You can always use the logic that I talked about in order to prove it, which only used triples in order to solve the puzzle. But I think it makes it more intuitive to spot those situations, especially if the band is roped. But if the band isn't roped, that's also something that you can sort of catch. Okay, so now I will actually solve this puzzle. So what we're going to start with is some easy cages that only have one possibility. So the 3, it is a 1, 2. It's the only way to do that. The 7, you can only do with 1, 2, 4. The 10, you can only do with 1, 2, 3, 4. And a couple more things to point out is the 12 cage must have a 1 and a 2 in it. And the way to think about that is, if we didn't have a 1 and a 2 in it, we could have a 1 or a 2 in it. And so let's try to make it as small as possible by making it 1, 3, 4, 5. But 1, 3, 4, 5 adds to 13. So, and obviously if we excluded the 1 instead of the 2, then our minimum is 2, 3, 4, 5, which adds to 14. So you have to have a 1 and a 2 at the 12. And so now a couple things to point out. One is this 1, 2. There's a 1, 2 in this row already, and there's a 1, 2 in this row already. And so in this box, the 1, 2 have to be down here. which means that this one can't be 1 or 2. So it's a 3 or 4. Additionally, this 7 here, there's a 1, 2 looking at this cell, and the 1, 2 is in the 12, which looks at this cell, which means that the 7 can't contain a 1 or a 2. So the only way to make 7 then is with a 3 and a 4. Okay, so it's at this point that we can use the logic that I talked about earlier, and we can look at whether this band is roped or not, or whether we don't know. Well, first of all, we know that if it's roped, it would be roped with a 1, 2, 4. So we could do that, 1, 2, 4 here and 1, 2, 4 here. That is possible. But is there a way to not rope? Well, if you remember, in order to not rope, we have to have, with the 1, 2, we have to have 3 distinct numbers. So here we have a 4, so we wouldn't be able to use the 4 anywhere else. Here we could use, say, the 3, but then here we wouldn't be able to use the 3 or the 4, and we'd have no options left. So another way to put that is we're either going to repeat 1, 2, 3 or 1, 2, 4. So if this were 1, 2, 3 and this were 1, 2, 3, that would force 1, 2, 3 here, but we know that's not possible because it's 1, 2, 4. So the only option is to repeat the 1, 2, 4 with one of these. Say, hey, this was 1, 2, 4 with a 1, 2, 4. Well, then that prevents 1, 2, 4 from being in these 6 cells and forces 1, 2, 4 down here. So that's the exact same roping logic that I talked about earlier. So this must be roped, and it must be roped as 1, 2, 4. And that immediately gives us some digits. That means this is a 4 and this is a 3, and this is a 3, and this does not contain a 3. So it's a 1, 2, 4. So now what I'm going to do is, we don't really need to color these because we already know what's in them, but I'm going to color the rest of these bands here. So what I'm going to do is I'm just going to use green and blue. So green here is this triple, and blue here is this triple. And if we follow this along, this green with the 1, 2, 4 means that this one's blue, which leaves this to be green, which leaves this to be blue, and this to be green. So that's the only way to color it. And what we can do is whenever we put a digit into the green, that means it must also be in the other 2 greens and can't be in the blues. And similarly, when we put a digit into the blues, that means it must be in the other 2 blues and can't be in the greens. So that's what the usefulness of having that coloring there. So the next thing to look at is now that we have this 3 here, we can see that it plays really well into this 20 clue because these 2 cells now need to add to 17. Well, in 2 cells, the only way to add to 17 is with 8, 9 because we can't repeat in the box. And so now this 18 cage, it can't use an 8 or a 9 in it. And so if we think about the maximum that we could be, which is 6, 7, 8, which is 5, 6, 7, that does add to 18. And so we just fill 5, 6, 7 in there. It's the only way to make 18 without 8 and 9. And then we have 3 digits left here. One of them's a 4, and the 4 can't be in these 2. So we can place the 4, and that leaves 1 and 2 left over here. Additionally, down here, this 12 cage now can't contain a 3. What's the lowest that we can put 4 digits without a 3? 1, 2, 4, 5. And that does add to 12. And so this is 1, 2, 4, 5. Because any other change to that would make it larger. And we can also look at this 12 cage. So how do we make 12 without a 3? Well, we just did that. It's 1, 2, 4, 5. It's the exact same logic. And so now we know this is 1, 2, 4, 5. The 5 is used in the row, which means the 5 can't be here. So this is a 5. And then here, these are the last 2 numbers for the row, which is 8 and 9. So now what we can do is look at the 16 cage. And we can think, okay, can this be an 8 or a 9? Well, let's try 9. So if this is a 9, then that means these 3 cells add to 7. Well, we know from this that the only way to make 7 is 1, 2, 4. And if I were to try to fill 1, 2, 4, that none of them could go in this cell because it sees 1, 2, 4 all over the place. And so it's not actually possible for this to be a 9 because we can't make 7 out of the rest of the 3. So this is an 8, and this is a 9. And what we can do is we can think about this 8 now. The rest of these 3 have to add to 8, which means they have to contain a 1. So there is going to be a 1 up here. And it's going to be either 1, 2, 5 or 1, 3, 4. But if we think about that, so that means the 1 can't be down here, right? And the 2 and the 4 can't be down here. So this cell is going to be a 3 or a 5 because it's going to be 1, 2, 5 or 1, 3, 4. And so if we think about it, if this is a 3, that means we're the 1, 3, 4 variant, and the 3 is down here, which means we need to have a 4 up here somewhere. And again, both of these can be 1, but the 4 would have to be down here. So the 4 would be here. If this is a 5, then we're the 1, 2, 5 variant, which means that the 1's with a 2, and that would be a 1, 2. Now, I would be wrong of me not to point out at this point that we could make a uniqueness argument and say that if this were the 1, 2, 5, then that would mean that this puzzle cannot be solved with a unique solution because the 1, 2's here would never get resolved. But we're not going to make that argument because I need to prove that this puzzle is unique without using a uniqueness argument. But if you want to shortcut it, feel free. I think the logic is interesting without shortcutting that, though. So the next thing to point out is because I marked 1s in one of these two, this one can't be 1, and this one can't be 1. I'm also going to just add a few more pencil marks here while we can. So these 4 are 6, 7, 8, 9, because that's what's left for the box. And additionally, if we look at this column now, where can 1, 2, and 4 go? Well, they can't go down here. They can go, obviously, 1, 2, 4 does go here somewhere. If you remember our roping argument, and also just for the box logic, 1, 2, 4 can't be in green or blue. This could be 1, 2, or 4. But on the top row here, we actually have a 1, 2 pair and a 4 placed. So 1, 2, 4 can't be in the top row. And so the 1, 2, 4 is limited to 3 cells in this column. So that's a hidden triple, which means this is a 1, 2, or 4, and this can't be 5. Because otherwise there wouldn't be enough space for 1, 2, and 4 in the column. So the next thing is to consider that now we have an additional 1, 2, 4 in the second row. So the first 2 rows have exhausted their 1, 2s, and 4s. So where does the other 1, 2, and 4 go in box 2? Well, it has to go here. So that's another hidden triple. So this can't be 5. So we've actually limited 5 to these 2 and 1 to these 3. Because 1 is limited to these 3, this one actually can't be 1. All right, so the next thing to point out is this 20 cage here. And we can think about what its possibilities are because we actually have a 1, 2, 3, 4 already in the column. So the thing to ask is, can we exclude a 5? The answer is no, because this would have to be 6, 7, 8 in order to exclude a 5 at minimum. And 6, 7, 8 adds to 21. And so that is too large. So we must contain a 5 somewhere in this 20 cage, which means there is no 5 in these 2 cells. Most importantly, this one here, which can't be 1, 2, 3, 4, or 5. And so it's a 6, 7, 8, 9, making a 6, 7, 8, 9 quadruple in the row. Now, if we combine that with the 1, 2, 4 in this column, those intersect in this cell down here, which can't be 1, 2, 4, 6, 7, 8, or 9, making it a 3 or 5, pairing up with this 3, 5 in the column, leaving just 3 digits, 6, 7, and 9, for this 38. Now, if you know anything about 38s and 6, which you may or may not, let's say you don't know anything about 38 and 6. It's actually easier to think about the inverse. So if you think about the numbers 1 through 9, they add up to 45. If we do 45 minus 38, then you get 7. And so we need to exclude 7 from the 6 digits that are here. And so in 3, we have to make 7. There's that 1, 2, 4 again. So we can't have 1, 2, and 4 in here. We have 6, 7, 9 already. And so that leaves just 3, 5, and 8 for these 3 cells. And this one sees a 3. So it can't be 3. That actually makes a 3, 5, 8 triple in the box. But more importantly, the 3 and the 5 actually look up into box 2, preventing 3 and 5 from being in these cells. These can't be 3 or 5, and so 3 or 5 in these 2, and there's only one way to do that, which is the 5 here and the 3 here. And so the remaining 2 in this column are 6 and 7. If we think about this cell here, where does it go in box 3? Well, it can't be in the same row. Whatever digit this is, can't be in this row, can't be in the cage, and it's 6 or 7, which is not 1, 2, 4, or 5, and so that leaves just one cell left. So this is also 6 or 7, and it's going to be the same as this one. Normally I'd color that, but it's not really necessary because it interacts with this 6, 7, so we don't really have to remember that. Whatever is here will force it to also be here. So the other thing to consider is in column 6, where does 9 go? It's missing from all of these cells here. And we have a 6, 7, 8, 9 quad that eliminates it from here. So that means a 9 is actually here in the blues. And if you remember, that means that all the blues have a 9 in them somewhere. So I'm just going to corner mark 9s into those so that we remember that. These 9 corner marks actually do eliminate 9 from this, which forces a 9 to be only in these 2 cells in this box. And additionally, if we think about this 3, 5 that we just placed, that eliminates 3, 5 from these cells here, which leaves a hidden 3, 5 pair right here. So this one can't be 8. And if we look at this row here, what's this cell? Well, we have 1, 2, 4 triple. We have a 6, 7 pair. We have a 3 and a 5. And so that leaves just 8 and 9 for this cell here. And now what we're going to do is we're going to look at this 37 little killer. We have most of the digits in it already. And let's look at what the minimums of these are. But first, I'm actually going to think about what numbers can actually go in this cell. So we actually have a 1, 2, 4, 5 quadruple in the column. And so we can't be 1, 2, 4, or 5. So this cell can be 3. And if it's not 3, it has to be bigger than 5. So it's 6, 7, 8, or 9. Now, let's add up these cells. Let's add up the minimum values for each cell. So starting here, we've got 3 plus 1 is 4, plus 9 is 13, plus 8 is 21, plus 3 is 24, and then plus 8 is 32. And so we need to get to 37 exactly. And so we would need a 5. If we use the minimums, we need a 5 here, which means we can't ever use anything higher than 5. And the only option that's not higher than 5, or sorry, that's 5 or lower for this cell is a 3. So it must be a 3. And that actually means that there must be a 3 in the others. But that doesn't mean we can prove this is a 3 yet. Actually, it does mean we can prove this is a 3 because there's a 3 in the column already. So that proves this one's a 3. And one of these is a 3. And if you remember in the 20 cage, 5 was our minimum number, and there's a 3 in the column, so the 3 is over here. And so additionally, we can now that we know it's a 3, we can look at this sum again. We can ask whether this can be an 8. So what we'll do is if you remember, with all these as minimums, well, let's just do the sum again, just so we don't get confused. So without this cell at all, we've got 3, 6, 9, 18, 26, and then if we add another 8, that's 34. And so with 34 total, in order to get to exactly 37, we need a 3, and we can't put a 3 here, which means 8's not possible, which means this is a 9. And so now instead of a 3, we need a 2 here, so this is a 2. So we can clean up some 2's in various places. And additionally, with this 9 placed, we can actually place this 8, this 9, and this 9 here cleans up the 9 from here. And so now we did place this 3 here, and we got a little distracted by finishing off this diagonal and a few other things. But placing this 3 immediately told us that this was a 1, 4, because 8 plus 3 is 11. We need to have 5. The only way to make 5 is with a 1 here and a 4 here. So that does resolve this 2 and the 1. This 4 resolves this 2, which means that this is a 1, 4, 5. So I can get rid of my little corner marks here. This is 1, 4, 5, which means that this one is a 2. Also do that from the row. And this one can't be 2. Next, this 3 also does give us the 5 down here. And this 5 resolves this 8, so this is 8. This 3 resolves this 5, so that's 5. This is 3. Sorry, there was a lot going on all at the same time, so you could resolve that in any order you feel like. Additionally, this 4 gives us a 2 here. And we can fill the 1, 4 down here just to finish the column. And notice we did place a 5 in the greens, which means we can now mark 5s in where they could go in the greens. It can't go here because of this 5. And additionally, because the 5 is in the greens, that means it's not in the blues, which means the 5 for the 20 cage is limited to box 7 in one of these two cells. And so the next thing we're going to look at is this 12 sum, this diagonal little killer. And so let's look at the minimums first. So this is minimum 1, and this is minimum 1, 2. So if we think about that, this is minimum 4, and so the maximum I can put in this cell to preserve the 12 sum would be 8, because 8 plus 4 is 12. And so that means the 9 isn't possible. So now there's only one spot for the 9 and now one spot for the 3. And so that actually does place the 3 down here because we have these 3s looking in. And this cell can't be a 3 because this 3 looks down as well. And so we can place this 3. And also we do have these 3s looking up here, so we might as well place that 3 as well and just finish all the 3s. So now we're going to be a little bit more careful about this 12. And what we're going to do is say, okay, what happens if this one's 8? Well, we know that this has to be 1, 2, and this has to be 1. It's the only way to fulfill that adding to 12. But let's think about this 17 for a second. What happens if this is 1? Well, if this is 1, then these two have to add to 16. And there is exactly one way to add to 16 and 2. That's 9 and 7. Otherwise, you'd have to repeat the 8 twice, which is not allowed in the row and not allowed in the cage. So this is 9, 7. But both of these cells see a 9. So they can't actually be 9, 7. And so this can't be a 1. So if this were at 8, the 2 would be here and the 1 would be here. And that does seem plausible. The other option is for this to be a 7. If it's a 7, then these need to add to 5. Let's say we preserve this as being 1. Well, then these would have to add to 4. Only way to add to 4 in two cells that can't repeat, because they're in the same box, is to use a 3. We can't use a 3. It would have to be 1, 3, can't use a 3. So the only other option is to use 1, 2 here, just like the 8 did, and put a 2 in here instead of a 1. And that would add to 4. 5, I mean. And then the last option is to have a 6 here, because we can't be a 5, because of the 5 in the greens, and we can't be 1, 2, 3, 4, and 9. So with the 6, these add to 6 as well. So how do we add to 6? Well, if this were a 1, then these would add to 5. One way to do that is 1, 4. Again, this one can't be 1, so the 1, 4 would go like this. And the only other way to add to 5 is 2, 3, and we can't use a 3. So what if we were a 2 here? The 6... to add to 2, to add to 6 in 3 with a 2 here, these would add to 4. How do we add to 4? The only way is 1, 3. That's not possible. The 3 is used. And so then the other question is, well, what if we put a 3 here? Well, we can't, because there's a 3 here. And obviously we can't put a 4 here because these would have to add to 2. There's no way to do that. So these are actually the only options. If you notice, that means that this one's a 1. That places 2 and 1 here. And the other thing we can point out here is there's a 1, 2, 4 left in the row for this because we have the 6, 7, 8, 9, and 3, 5. And it can't be a 1, so this is a 2, 4. So we do end up with a 2, 4 pair in the column and in the box. So now what we're going to do is we've limited this cell to 2 and 4, so let's look at the 17 cage. And we're just going to go through the options again. So if this were a 2, what would the 17, these two would add to 15. So how do we add to 15? Well, we already know we can't use a 9, so 9, 6 is out. The only other way to add to 15 is 7 and 8. But also, if you notice, we also can't put an 8 into either of these cells. This 8 sees this one, this 8 sees this one. So we also can't be 7, 8. So actually 2 isn't possible. So we are a 4. So that makes this one 2, this one 1, this one 4, 1 and 4. This sum now sums to 6, which means this is a 6. We now have a 6 in our blues, so the 6 goes here, and this is a 6, 9 pair. We now know there's a 6 and a 5 in the 20, So that means that it's 6, 5, 9 in order to add to 20. So this is going to be 5, 9. And additionally, we can look at our 17 sum and see how that can be fulfilled. So we have 4 already, which means these two add to 13. We can't use 9, we can't use 8. And so the only way to add to 13 would be with a 6 and a 7. And the 6 here tells us the order. So this is a 7 and this is a 6. That tells us the order of these two. Additionally, we know we need a 2 more values for this column. That's a 2 and an 8. The 2 can't go in this box, so the 2 goes here. And that makes this an 8. And also what we can do is this 6 gives us the 7. So we now know the green is 5, 7, 8. We've actually known that for a bit. So 5, 7, 8. This one can't be 5. This one can't be 7 or 8. That places the 5 and leaves a 7, 8 pair here, which cannot be resolved. This is, sorry, this can't be 6 or 9, so that's also the 7, 8 that pairs up with it. This cell here is also a 7 or 8, and up here in the greens, this is also a 5, 7, or 8, and I don't think anything resolves that yet. We'll deal with that later. So the next thing I want to point out is this cell here. Where does it go in this box? Well, it's a 7 or 8, and it's not in these 3. So that means these two are identical. And this cell here sees a 7. So that means these are both 8. And then this is a 6, 7, 9 triple. That means this can't be 8. So next we can just clean up more pencil marks. So this can't be 7, and this one can't be 6. So this is 9 and 6. Just finishes off the box. This 9 gives us the 5, 9. This 1 here eliminates these ones. And here there's actually just a pair left. So we can actually make it 2 and 1, and that we know the order of them as well. This is a 4, 5. This 1 eliminates this one up here. And of course we have this 7, this 8, and this 7. So sorry if you've been staring at those, I'm just getting around to them. All right, so next we will look at box 3. We should be able to finish it. So we need an 8 in the box. This 8 sees up here, can't be anywhere else, so that puts an 8 here. That means we can finish off the 26 sum. If you do the sum, you'll see that it has to be a 6. This is a 7, this is a 6. That resolves our clone that we saw a while ago. And there's just one more value for the box here, which is 7. And we can do a little bit of cleanup. Just getting rid of that 7 there. I'm not too concerned about it because we're basically done with the puzzle. But I think that's the cleanup we can get done. Oh, this 8 C's here, so that's 7 and 8. This 7 means this is 6, 7, and 9. This is 6 and 9. And at this point, this is kind of a deadly-ish pattern. So how do we resolve it? Well, there is one little killer we haven't looked at yet, which is this 54. And I'm not going to do this in front of you, but you can believe me that these sum to 53, which means that this has to be 1, 4, 5, 4, 1, 5, and 4. So that is how you solve Killer Blister. I hope you enjoyed the puzzle. I really enjoyed setting it, and I managed to preserve the opening that I wanted, which made me pretty happy. I've never set a killer before, so hopefully that didn't show. But yeah, again, I hope it wasn't too difficult for you. It wasn't intended to be that difficult, but maybe interesting would be a better word. Like lots of triples and quads, hidden triples. We had the interesting opening with the ropes. If you noticed the ropes, it did make the solve a bit easier. I don't know, maybe you saw the uniqueness argument, decided to use that, which would have resolved the 16 more quickly, gotten you the solve more quickly. But yeah, let me know in the comments how you did, and whether you enjoyed it. And if you do enjoy my content, don't forget to subscribe. Lately, I've been doing a live stream every week. For me, it's Saturday. If you're anywhere east of the Americas, then it's going to be very early your Sunday. I think with daylight savings time, it's now going to be starting at 2 a.m. UTC every Sunday, which on the West Coast in the US with daylight savings time is 7 p.m. Pacific time, 10 p.m. Eastern time, and again, 2 a.m. UTC. So whatever that translates to in your country, please feel free to do that translation. And additionally, usually around Thursday or Friday, I do put up a pending stream, which should show up in your feed if you're subscribed, and you can use that to check in their local time when that stream will be. So again, hope you enjoyed this, and I will hopefully see you in the streams, in the comments section, and maybe in the Cracking the Cryptic Discord. And until next time, thanks for watching.